Here we are in Lesson 7. Today we're going to look further into the Lagrange error bound and the accuracy. So far we've studied a lot of different ways to approximate functions, whether it's been graphically, tangent line approximations, Euler's method, and now we're looking at Taylor polynomials. We defined Taylor polynomials in the beginning of the unit of this chapter, and it's a good idea now to figure out how accurate our approximations are to the exact values in an infinite series. And we define that concept of the remainder this way, where the exact value of the function is the Taylor approximation plus some leftover remainder. And we define the error to be the absolute value of the remainder, which was the difference between the exact and the estimate. So we've already seen some of those cases. Let's take a look at the picture. When we use a Taylor polynomial that I'm describing as t sub n of x, centered at some c value, to approximate a function at a value, which is near the center, we can say that if the function is the polynomial approximation plus the remainder, then the remainder is the actual value minus that estimate. And you can see here my blue graph is my actual function, and we've approximated it with a Taylor polynomial that I'm calling p of x. Its center is at c, but we've moved over some distance and evaluated at a. So this gap here in between at the actual value and our estimate value, that's our error. Now, if you'll go with me over to the vocabulary page, I want you to think about this picture while we fill in some vocabulary. You see, if we added some values to that Taylor polynomial, this red line would get closer to the actual function, and our estimate would be more accurate there. So let's go find those vocabulary terms. Let's see where they are. So in this vocabulary, set 4, 2 facts about the error of that remainder. First, if we increase n by adding more terms to the polynomial, the remainder will get smaller in size. It's going to decrease in size based off that graph. And second, as we move away from the center of the polynomial, the size of the remainder will usually increase. So the farther away from the center, we're going to increase. Now let's go back to where we were. So in order for us to use Taylor polynomials effectively, we will use Taylor's theorem to estimate the size of the error. We saw that in the last lesson. The remainder given in the theorem is called the Lagrange form of the remainder, or the Lagrange error bound. And this gives us a bound for the error, but it doesn't give us the exact value of the error. We already looked at this definition last lesson, and you can see here that the function f of x, this is the approximation part. This is our Taylor polynomial. I'm going to call that the approximation part. And then this is the remainder or the leftover here. So this is kind of like a review from last time. And this part here, this is my maximum, the next derivative, the n plus 1 derivative at my a value. This is the maximum. So we said f of x, which is the actual function, is the Taylor polynomial, or my polynomial approximation, plus my leftover. That's the remainder at that value. Instead of finding the exact error of our approximations, we'll use these two rules that help us find the upper bound for the error. In this way, we'll know the most that we will know the most that our approximation is off the actual mark. And the two rules are, if the series is an alternating series, the error will be no greater than the absolute value of the first unused term. We saw that rule already in use in this unit. And if we have a non-alternating series, it's approximated. We want to use Taylor's inequality theorem, which we're calling Lagrange form of the remainder. And we have that stated below right here. So the Lagrange form of the remainder says this. If we have the remainder, it's going to be less than or equal to m. This is my maximum value. And we said the maximum value was going to be found by taking the derivative of the n plus 1 term at my a value, where we're between x and c is being the center. Bounds on the remainder found using this form are called the Lagrange error bounds. Now let's go look at vocabulary check number 1. So we just found the capital M represents the maximum absolute value of the n plus 1 order derivative of the n plus 1 order derivative on the interval between x and c, or c and x, and we can find the maximum by substituting the a value that's between x and c. That maximizes the expression f to the n plus 1 derivative at a, and we want the absolute value of that. Okay? And we called this the Lagrange error bound. When n is 0, Taylor's theorem states that if a function is differentiable in an interval containing some c, then for each x in the interval there has to exist between a and x and c. There exists a between x and c such that this occurs, and we ought to recognize this. So here's our actual function. This is the first function value at my c. This is the derivative, and this is the first derivative, and then x minus my center. If we solved for this derivative, you would subtract f of c from f of x and divide by x minus c. And doesn't that look a lot like the mean value theorem? We're taking that average. Let's fill in the rest of the vocab. The expression absolute value of x minus c to the n plus 1 power divided by the quantity n plus 1 factorial. Remember, we said this represents the first unused term, which is n plus 1 in our Taylor series. So this is the first unused term, which would be the n plus 1 term in your Taylor series. Now it could be a Maclaurin series, and then you wouldn't have the x minus c, you would just have the x. But if you have this expression, it's the first unused term. And the product of that first unused term times the derivative of the first unused term maximum of that is going to tell us a safe upper bound. It will give us a safe upper bound for the n plus 1 term, or the n plus 1 derivative. A safe upper bound for the n plus 1 derivative at some value x equals a, where a is between x and c. Number 3, if the maximum of that first derivative of the first unused term on the interval between the center c and our a value is not given or it's not easily found, then we'll be able to choose the first known reasonable number that's greater than that unused derivative or that n plus 1 derivative. Then we're going to choose the first known reasonable value. I'm going to say first, choose the first known reasonable number greater than that derivative. And if you don't know the maximum or the interval, we can assume the interval is from the center to the x value we're using. And I think that's the end of the vocabulary, just kind of formalizing this idea here. So let's give a few of these a try. If the function f has continuous derivatives for all real numbers x, we want to assume these given facts. And you can tell by looking at the given that our c value is 3. So our expression is going to be x minus 3 to some power as we create a third degree Taylor polynomial. So putting together a third degree Taylor polynomial, in x we want the f of our c plus the f prime of our c times x minus c over 1 factorial plus our f double prime of c times x minus c squared over 2 factorial. And then finally our last term would be the f triple prime of c times x minus c to the third power over 3 factorial. And they've given us this information so we can put that together. You can call it a Taylor polynomial or a p sub 3 for just polynomial, p sub 3 of x. So our f of 3 is 5. And then f prime of 3 is positive 2, so we have positive 2. And our x minus 3 to the first power divided by 1 factorial. Then our next term is the second derivative. The second derivative at 3 is negative 4. So negative 4 times x minus 3 to the second power divided by 2 factorial. And then our last term is going to be the third derivative, which is positive 3 times x minus 3 to the third power over 3 factorial. Now, what do they want us to do with that? They want us to use our Taylor polynomial and approximate the function at 3 2/10. So that might need a calculator. So let's give that a try here. We want to move this up. And we're going to look at the function value at 3.2 can be approximated by our Taylor polynomial, our third degree Taylor polynomial at 3.2. So putting all this together, we've got 5 plus 2, and 3 2/10 minus 3 would be 2/10. And then coming across here, we got 4 over 2 factorial, which would be 4 divided by 2 times 2/10 to the second power. And this is 3. And, oh no, it's not 3, it's 7. Just about to mess up there. This would be 7. And divided by 3 factorial would be 6, and then again 2/10 to the third power. So with our calculator, 5 plus 2 times 2/10 minus 2 times 2/10 squared plus 7 times 2/10 cubed divided by 6 is roughly 5.3293. Okay, so that was pretty simple. In part B, the fourth derivative of the function f satisfies the inequality that says the absolute value of the fourth derivative at a is less than or equal to 35 for all the x in the interval from 3 to 3.2. Use this information to find a bound for the error that we found in A. Okay, so that's telling us that the absolute value of the remainder of our polynomial at 3 is going to be the fourth derivative at A times x minus 3 to the fourth divided by 4 factorial. And that's got to be less than, this is our maximum here, so 35 is the maximum, times x minus 3 to the fourth divided by 4 factorial, the absolute value, on the interval from 3 to 3.2. So we found this formula back here, our Taylor inequality. The absolute value of r sub n of x is less than or equal to the derivative of the n plus 1 term at a divided by n plus 1 factorial times the x minus c to the n plus 1. Okay, so that's where that came from. So basically this term here, 35 is our maximum, and we've got 3.2, because that was our value in part A, 3.2 minus 3 over 4 factorial. And with our calculator, this is about 0.00233. So this is my bound for the error. And we're going to use that here in a second. So find an interval, part C, such on A to B, such that A is less than the function value at 3.2, which is less than or equal to the function value at B, and give 3 decimal places. In part A, we had 5.32933, and our bound was 0.00233, and we had 5.32933, and we want to subtract the bound 0.00233. So a little calculator work, and we have 5.327 is our A value. So the function, the actual function value has to be between 5.327 and 5.332. So we took our value that was the estimate in part A and added the error bound from part B, and we found the interval from A to B where the actual value has to occur. So can the actual value equal 5.331? Well, yes it can, because 5.331 falls in between our A value and our B value. Can 5.332 equal? No, it's not on the interval. The error would be altered then. I'll let you write your own explanation for that. Example 2, estimate the sign of a half using a Maclaurin polynomial. What's the least degree of the polynomial that assures an error smaller than 0.001? So here we're really being asked what's the smallest n where the remainder at a half is less than 0.001. That's our real question. That's the big idea. So we know, let's see, we know sine, the maximum for sine is going to fall between -1 and 1. So our maximum is got to be 1. Maximum has got to be 1, since we know that. And our formula says the absolute value of the remainder at our value, a half, has to be less than or equal to the maximum, which is 1, times our half to the n plus 1 divided by n plus 1 quantity factorial. That's our remainder, and that's got to be less than this value, 0.001, okay? So the remainder has to be the maximum times the next value divided by the next value, or this missing unused term. It's got to be less than 0.001. So the easiest way for right now, I think, would be to make a table where we're going to figure out if n is 1, and we're going to use this expression here, 0.5 to the n plus 1 divided by n plus 1 quantity factorial. So let's see how that goes. We're looking for a number that's going to be smaller than that, less than that. So when n is 1, you have a half to the second power divided by 2 factorial, which becomes 0.125. So we know that's not good enough. 2's not going to be good enough. We're going to have a half cubed divided by 2 plus 1 factorial. That's 3, which is 0.125 divided by 6. And that's not close enough. When n is 3, we have a half to the 4th power divided by 4 factorial. And this is 0.0625 divided by 24. And that is getting closer. And when n is 4, we have a half to the 4 plus 1 power divided by 5 factorial. And that's 0.03125 divided by 120. That's 0.00026. Bingo, we found it. So what we know is when n equals 4, that's the smallest n, or what the example said, the least degree where the remainder of the 4th degree at a half is less than 0.001. So our answer is a 4th degree. In example 3, we're going to let the polynomial be a 3rd degree Maclaurin polynomial. So right now we know the clue that our center is at 0. And we're going to use the information of the graph. And the graph is the 4th derivative. And we want to show that the remainder is less than 1 over 400. See, this is the remainder. So there's no interval that's given, and there's no maximum that's given. So we're going to do what vocabulary, the 3rd vocabulary sentence told us. If we don't know a value that is given or easily found for the maximum, then we can choose the first known reasonable number greater than the remainder's derivative. And in this case, the 4th derivative, it's telling us that when x is a 4th, if this is 1, here x is a 4th. So it looks like when x is a 4th, y is 10. So the reasonable estimate would be the maximum here at our center, and we're going to call 15 our maximum because no interval's given and no maximum is given, and we want to use the graph of the F4 of x, where the center is at 0. Our maximum would be 15, and that's what our vocabulary is calling a reasonable value. It's a reasonable value because it's greater than the derivative value of 10. So let's think about this. How can we put this together? The r sub 3 of 1/4 has to be less than 1 over 400. And this value is the maximum, which is 15, and we're the fourth derivative, so over 4 factorial, and our x minus c is going to be 1/4 minus c, but c was 0. Our c value, we're centered at 0 to the 4th power, and we want that absolute value. Again, I'm taking this formula back from the beginning of the lesson. So without a calculator, let's think about 15 can be 5 times 3, and 4 factorial is 4 times 3 times 2 times 1, and 1/4 to the 4th power, we can put that 4 to the 4th power down below. Think of that as 1/4 to the 4th power. So the 3's would be removed, and we would have 5 in the numerator and 2 times 4 to the 5th in the denominator, and we want this to be less than 1 over 400, correct? So we're asking, is this less than 1 over 400? Less than 1 over 400. And with our trusty calculator, you can tell by just expanding that, that's definitely less than 400. And if you needed that decimal approximation, you can see that yes, this is less than 400, definitely yes. So we could state that, therefore, the absolute value of the remainder at 1/4 is less than 1 over 400. So that's true. So this is a long lesson. We still have 2 more full examples. In this example, we want to make the note that if an error calculation is required on the AP exam, all the work must be shown so that the calculator can only be used as a method to check your computations. Here in example 4, we're going to use a Maclaurin series for y equals e to the x to estimate 1 over the square root of e, and we want that estimate to be accurate to 4 decimal places. So that's similar to example 2. And we know from last lesson that I said you need to memorize the sigma notation for e to the x. And if we wrote that out with 1 over the square root of e, then I'm thinking e is to the negative half. So we want to use this value here. And what I'd want to do is pull the -1 out to the front, make it its own separate expression to the n power, and use 1/2 to the n over n factorial from my formula here. So we're going to work it that way. Now, if you want, you can make a table and figure out all the calculations. But I'm going to look at, let's see, to 4 decimal places. So I think we're going to have to probably use 5 or 6. So P sub 5, so my Maclaurin series at 1/2. And again, I'm using this summation formula. Okay, so we want to write a 5th degree polynomial. And using this formula, we have 1 minus 1/2 plus 1/2 squared over 2 factorial minus 1/2 cubed over 3 factorial plus 1/2 to the 4th over 4 factorial minus 1/2 to the 5th over 5 factorial. So now, with this last expression, if you think about, I'm going to change variables so I don't use n again, but if you think about 1/2 to some value k divided by k factorial, what this question is asking us is, can we get a value that's less than 1, 2, 3, 4? So we want to be accurate up to the 4th decimal place. And this is the maximum error since it's an alternating series. So because it's an alternating series, you might want to make a note of that. It's an alternating series. So in an alternating series, we said the error would be less than or equal to the first unused term. So our k would be 6, and we can use p sub 5 to the half, and we could check that with the calculator in school, but we can't do that on the AP exam for verification. So if you checked it, the 6th term, 1/2 to the 6th power divided by 6 factorial would be, from our formula, -1 to the 6th, so that would be positive. And 1/2 to the 6th power would be 1 over 64. And 6 factorial would be 720. So we would be looking at 1, positive 1, divided by 46,080. And on our calculator, that's 1, 2, 3, 4 zeros and 2170. So it is definitely accurate to 4 decimal places. And if you checked with your calculator, e to the -1/2 power is about 0.6065306. And our 5th term, this term here, in our Taylor polynomial, is about 0.6065104, and the difference is this value, the unused term, 34202. So there we have example 4. And our final example, using the Maclaurin series for cosine. So we know the cosine of x is the summation from n equals 0 to infinity of -1 to the n, x to the 2n, because they alternated on evens, and 2n quantity factorial, which works out to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and we want this 4th degree. So here's our 4th degree polynomial, and we want to use it to compute the cosine of pi over 12. So cosine pi over 12 is going to be 1 minus pi over 12 squared divided by 2 factorial plus pi over 12 to the 4th divided by 4 factorial. And using our calculator, cosine of pi over 12 is approximately all of this, 0.96596272919. All right. and you can check it. I think it goes off on the calculator. The calculator value is 965,925. So it goes off right here. Part B. Use the Lagrange error bound to show that the remainder is less than 1 over 5,000. So we want the f of pi over 12 minus the approximation at pi over 12 to be less than 1 over 5,000. So we know that the upper bound on any given interval for sine or cosine is 1. That tells me our maximum is 1. Our x value is pi over 12. And our center is at 0 because they told us it was a Maclaurin series. So the remainder of our fourth degree polynomial at pi over 12 is going to be the absolute value of the maximum times our x, which is pi over 12, to the fifth power, because it's n plus 1, divided by n plus 1 factorial. And using my calculator, something changed there. Oh, try that again. I got 4 zeros, 1, 2, 3, 4, and then 1, 0, 2, 4, 8. I'm going to call this value A. Value A. So we got 1, 2, 3, 4, and then 1, 0, 2, 4, 8. That's got to be less than or equal to 1 over 5,000. And I'm going to call this one value B. So this value in my calculator, 0.000010248, has to be less than or equal to 1, 2, 3, and a 2. So yes, that's true. 1, 2, 3, and a 2 starts here. So therefore we could say value A is less than value B because A is defined to be the absolute value of the exact minus our approximation with our Maclaurin series. Okay, so the reason I'm doing this here is so on a FRQ on the AP exam, I can establish A is this value and B is this value so I don't have to write them out over and over. Part C says use that fourth degree Taylor polynomial for cosine about 0 to find an approximation for cosine at 8/10, and then use Taylor's theorem to determine the accuracy of the approximation. So the cosine of x, we know the cosine of x is about the Taylor fourth degree polynomial, which was 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. And the cosine of 8/10 is approximated by the Taylor polynomial at 8/10. And if we substitute there, we've got 1 minus 8/10 squared divided by 2 plus 8/10 to the fourth divided by 24. And this one I'm going to actually store it in the calculator. It's 0.697066. And I want to write, if this was an FRQ, I'm going to write that I'm storing that value in A. And we know that the error, because again, it's an alternating series, so the error is going to be the next term because it's an alternating series. So the error absolute value has to be less than or equal to the next term. which means the cosine of 8/10 minus the 4th degree approximation has to be less than or equal to our value at 8/10, and the next term would be the 6th power over 6 factorial. And we need our calculator for that. And again, I'm going to store that. So this value here, I got to go to the next line. 3 zeros, 3, 6, 4, 0, 8, 8, and I'm storing that in my calculator as value B. So now we can answer part D. Can we find the interval from A to B such that A is less than or equal to the actual value of cosine, and that's between less than or equal to B? So just like we did in the previous example earlier, which example was that? Lost it. That was example 1, just like in the previous. If we have the cosine, the actual value is less than or equal to, and then I would do A plus B, and less than or equal to A minus B. So if you stored these in your calculator, we've got 69706 repeating minus 0.000364008. So do that arithmetic, and we would end up with 0.6967025 is less than or equal to the cosine of 8/10, which is less than or equal to, and same deal over here. Let's add them this time. So first we're subtracting them, then we're adding them. And this would be 0.697430075. So the actual cosine is between this value and this value. And I'm writing so big I don't have room for my zeros. That's a long lesson. Maybe good to break that up into 2 days.